Select the major product of the following reaction. So we can see that we have a ketone as our starting material. And we are reacting this with trace acid, so this is just slightly acidic conditions. And a secondary amine. And so what we might recognize here with these conditions is this looks like what we have talked about previously, making an enamine. So let's go ahead and we're going to look at that, and then we're going to come back to the fact that we also have another reagent in here that will change the reaction slightly. So we are going to look at if we took a ketone, and if we just had that trace acid and the secondary amine, we would form the enamine as a product. And so what we saw previously is that we can simply take the nitrogen of the amine and basically snap it in place right there where that oxygen was of the ketone or aldehyde. In this case, it's a ketone. And so let's go ahead and draw that. And so we're going to replace that double bond to oxygen with a double bond to this nitrogen right here. And then that nitrogen has a methyl group and an ethyl group. It also has a hydrogen. Protons are easy to remove, so that will get removed in the course of this reaction. But the nitrogen carbon bonds will not be cleaved. So we would still have that methyl group, and we would still have the ethyl group. And of course, a positive charge on the nitrogen. And so to get rid of that positive charge, what would happen is you would remove a hydrogen from the alpha carbon. So when we say alpha carbon, we mean the carbon that is next door to the initial carbonyl. So this would be an alpha carbon, and over there would also be an alpha carbon. So what's going to happen is some base that you have present in solution would remove one of those two hydrogens. The electrons would come in to form the double bond and shift these pi electrons up onto the nitrogen, thereby neutralizing that negative charge. And so you would form the enamine, the structure that contains the alkene, so it would be here, and the amine. So that is an enamine. And so that would be the final product of this reaction if we only had the acid and the secondary amine. And so that would be the product if we didn't have this sodium cyanoborohydride. So with no of this sodium cyanoborohydride. So we need to recognize what happens when we do have that sodium cyanoborohydride in there. So what this is, it might look a lot like sodium borohydride to you, and that would be a good way to start thinking about this. And recognize that this is also a reducing agent. And so what this is this is a mild reducing agent. So it's even milder than sodium borohydride. So milder than sodium borohydride. So that means it will not reduce an aldehyde or a ketone. So we can throw this, notice this is all being thrown in at one time. We do have our reagents spread out above and below the arrow, but there's no numbers to indicate that these are sequential, so that means we're actually just putting this all in the flask at the same time. So this, we don't have to worry about it reducing the ketone, because if we reduce the ketone, the reaction, of course, wouldn't work. So that's why we're using that milder reducing agent. So this will not reduce aldehydes or ketones. So here's what's going to happen if you've got that sodium cyanoborohydride in there. So you could think of it just reducing your enamine. The more likely species that's going to react with is actually this iminium ion, because that's even more electrophilic there. So what would happen, so you are going to reduce it to get this product overall. So your answer is going to be D. But let's just show how that happens. So I'm going to redraw this iminium ion here, because we know how that forms. And then we're just gonna take a look at that reducing agent and how it could react with this aminium ion. So sodium cyanoborohydride looks a lot like sodium borohydride. It's just that we have only 3 hydrides that can be donated, and it's having this electron withdrawing cyano group that makes it a little bit less reactive, okay? So not as reactive as sodium borohydride. And sodium borohydride is, of course, your milder of your 2 main reducing agents that we've talked about. So we can see how this can react. So we're adding a hydrogen right here. So we'll say that's the hydrogen right there. It's going to push that pi bond, the lone pairs, onto the nitrogen. And so that's how you end up with the reduced product that you see in D. So overall, this process, you're doing a reduction and you're adding nitrogen. This overall reaction is known as a reductive amination. So you'll recognize this because it's going to look like your conditions to form an imine or an enamine, but then you're also going to see that additional reducing agent in there.